The RL78 MCU family offers low power operation in every mode. These are current drain comparisons of RL78 against competitors A, B, C, and D. In run mode, the RL78 can consume as little as 66 microamps per megahertz when running no-op instructions, which means the CPU can be idle waiting for an interrupt at a very low power consumption while in operating mode. Even when running an all-instruction mix, RL78 power consumption is 144 microamps per megahertz typical, which places RL78 in a best-in-class category. In halt mode, this suspends the CPU but allows all peripherals to run. This mode maintains the system clock that was running before the time halt mode was entered. Then CPU operating mode can be quickly reestablished without having to wait for the system clock to start up. This halt mode graph is a special case comparison where the 32 kHz subclock is not only running the RTC real-time clock, but is the system clock to run the suspended CPU when run mode is resumed. In this combination, a modest current drain of 0.57 microamps typical is being drawn, with all RAM data retained and LVD reset function enabled. For stop mode, in this typical comparison, the watchdog timer and low voltage detector, like the POR, are both operational with all RAM data retained, but drawing a mere 0.53 microamps typical. This stop mode current also includes the current drain of the 15 kHz low-speed on-chip oscillator clocking the watchdog timer. RL78 has a power management system that facilitates efficient use of the power supply, critical for optimizing battery life in portable applications. In CPU run mode, the on-chip oscillator can be scaled down to lower frequencies to save MCU current if maximum CPU performance is not required at that moment. Changing over to halt mode can further reduce the MCU current drain, allowing full peripheral operation while suspending CPU code execution. Halt mode can save as much as 80% of the total MCU current compared to having the CPU running. For example, RL78 achieves 5.1 milliamps current drain in run mode at 32 MHz versus 1.1 milliamp in halt mode, also at 32 MHz. In stop mode, the 15 kHz low-speed clock and 32 kHz subclock can still run, enabling the operation of the real-time counter for date time and the LCD controller driver boost circuit, as well as 8-bit or 12-bit interval timers for timed events. Additionally, the watchdog timer and the low-voltage detect circuit and external interrupts can be enabled. All these stop modes peripherals are low power and draw less than 1 microamp total. Then, RL78 adds a special low power mode that didn't exist on previous low power MCU generations called the snooze mode. Serial ports like SPI or UART or the ADC converter can be enabled, but suspended and waiting for incoming data while in stop mode, and be prepared for fast peripheral wake-up. The snooze mode enables the serial ports or the ADC converter to start up with a high-speed on-chip oscillator clock operation from stop mode, but without clocking the CPU. Therefore, snooze mode is similar to halt mode in that no CPU intervention is needed until after the data is captured, thus saving current drain. This page highlights the scalability of the 16-bit RL78 MCU family, both in code flash memory sizes as well as pin count scaling with 14 different pin counts from 10 to 128 pins. The color coding at the top is for different RL78 series types. A series with G denotes a general-purpose RL78 MCU, but with some optimized feature set, for instance like G1D Bluetooth Low Energy or G1H sub-gigahertz RF transceiver. An L series denotes LCD controller driver function. An I series can denote industrial, inverter, lighting, metering, or detector application types. You can easily expand from the smallest to largest code flash size within the same series. If you start with a small pin count RL78 MCU, you can add more pins without having to rewrite the previous code drivers already written and debugged. For example, any I2C, UART, or ADC driver software that works on a small RL78 pin count will work without coding changes on larger pin counts, even across the different RL78 series types. Package types are as small as 3x3 millimeters for the 25-pin LGA or 4x4 millimeters for the 36-pin LGA. Regarding RL78 pin compatibility in peripheral pin I/O redirection, on RL78's I/O port pins and peripheral function pins scale up from the smallest to the largest pin counts while maintaining the logical port pin numbering and keeping the peripheral pin physical printed circuit board layout in the same order position as the pin count is increased. The color-coded pins are an example of actual I/O port commonality from a 20-pin SSOP up through the 80-pin QFP package version. On the other hand, the PIOR, which stands for Peripheral I/O Redirection Register, capability allows the designer to optimize the peripheral pin functionality by remapping the physical pin's connectivity to a chosen peripheral. In this real-life PIOR example, using an RL78 and 64-pin QFP, the default setting is I2C interrupt pins and timer channel 0 I/O pins mapped on a subset of the QFP pins 17 through 32, which are shared with other peripheral functions mapped there. Due to a layout constraint or peripheral pin sharing constraint, there may be conflicts for existing peripheral I/O pin assignments. In that situation, port I/O redirection can help ease the bottleneck, as shown in this case, by remapping the I2C interrupts and timer functionality to QFP pins 33 through 48.